Okay, Assalamualaikum. Good morning everyone. Semua boleh dengar? Okay, semua dengar suara saya? Okay, Assalamualaikum. Good morning. Okay, so hari ini kita akan dengar.
Dengar.
Okay, so hari ini kita akan masuk chapter baru, strengthening mechanism. Okay, so we already discussed in previous chapter. We know that when we increase the dislocation density, we increase the yield strength, which result in a higher shear stress required to move the dislocation. Okay, so hardness and strength are related to how easily a metal plastically deform. So when we reduce the dislocation movement, the mechanical strength can be improved. So this topic is we can say is an extension of a dislocation concept that we have learned before. Okay, topik ni macam sambungan lah daripada topik dislocation yang kita dah belajar dalam last week tu. Okay, hari ni saya briefing singkat je sebab saya dah rakam semua lecture untuk topik ni. Okay, dalam chapter ni kita akan bincang tentang mechanism of strengthening material or specifically metal. Okay. Okay, tugas kita sebagai material engineer, it is our responsibility to design alloy that have a high strength and yet some ductility and toughness. Okay. What do you understand by a strengthening mechanism? Strengthening mechanism refers to mechanism to strengthen metals. So we need to control the strength, toughness, and ductility. And usually strength is in inverse relationship with ductility. Okay, so how we can relate between strength and ductility? Okay, let's say kita ada strength. Okay, strength and ductility. Okay, how can we relate between these two? Okay, usually strength is in inverse relationship with ductility. Okay, bila strength naik, when we increase the strength, then ductility will decrease. Okay, when we increase the strength, that ductility will decrease. And vice versa, when we increase the strength, and when we decrease the strength, ductility will increase. Okay, itu dia punya relationship between strength and ductility. Okay, this one saya skip je. This is just some introduction to strengthening mechanism. So strengthening mechanism is the relation between a dislocation motion and mechanical behavior of a material. So topik ni very related to dislocation concept that we have learned before. Okay, in previous chapter, what we have learned. Okay, we already learned that the ability of material to plastically deform will largely depend on the ability of dislocation to move. Okay, ability of material to plastically deform depend on the ability of dislocation to move. So what happened if we reduce the mobility of dislocation? Okay, what happened if we reduce the mobility of dislocation? Will the mechanical strength be enhanced or reduced? What happened agak-agak if we reduce the mobility of dislocation? What happened to the mechanical strength? Okay, itu you jawab sendiri. And what happen when we unconstrain or we limit the dislocation motion? What do you think will happen? Okay, the answer we already learned in previous chapter. I hope you already understand this concept. If you understand the concept of a dislocation, then there will be no problem to predict what happened when we reduce the mobility of a dislocation and what happened when we limit the dislocation motion in terms of mechanical strength and the density of a dislocation. Okay, the key point to remember, the first one is it is very important to the understanding of a strengthening mechanism is the relation between dislocation motion and mechanical behavior of metal. So because microscopic plastic deformation correspond to the motion of a large number of dislocation, the ability of metal to plastically deform depend on the ability of dislocation to move. Okay, because hardness and strength, both gill and tensile are very related to the easiness of a plastic deformation can be made to happen. So when we reduce the mobility, okay, of dislocation, the mechanical strength may be enhanced. Okay, when we reduce mobility, bila kita limitkan pergerakan dislocation ni, mechanical strength of metal, for example, will be enhanced. But when we increase the mobility of dislocation, what happened, do you think? Okay, the strength will reduce, but the ductility of that material will increase. Okay, so greater mechanical forces will be required to initiate a plastic deformation when we reduce the mobility of a dislocation. Okay, so virtually, mostly all the strengthening technique rely on this simple principle. So you have to remember this principle when we restrict or hinder ataupun limit. Bila kita limitkan pergerakan dislocation, when we limit dislocation motion, we will produce a harder and stronger material. This is the key point that you have to remember. So when we make the material harder and stronger, that is why this topic is called strengthening mechanism, because we want to increase the strength of this material. The strength of material, we can increase it by hindering, by limit. Okay, by limit the movement of dislocation responsible for plastic deformation. So there are different ways if you want to limit dislocation motion. For single phase material, include a grain size reduction, solid solution strengthening, and strength hardening. Okay, for multi-phase material, okay, among the mechanism that can be carried out maybe include precipitation, strengthening, okay, dispersion, strengthening, and martensite strengthening. But for this topic, for this particular topic, we just concentrate on this mechanism. So this is all the mechanism that we have to remember if we want to improve the strength of that particular material. The first one is a grain size reduction. Okay, kita kurangkan jumlah size size grain dia. Tahu grain kan yang macam ni tu? Okay. Okay, kita kecilkan size dia, and then also solid solution alloying, strength hardening, or kita panggil dia as a cold working, and also precipitation hardening. So these are four mechanisms that you have to understand for this topic. Okay, among the method that we can do to strengthen the material is by, like I have mentioned before, by reducing the grain size. So we can see this is the example of a grain. This is a grain. A grain size in polycrystalline material will affect the mechanical properties. So here we have a grain boundary. Okay, masih ingat grain boundary? All these are grain boundary. And this grain boundary will act as a, dia macam sempadan ini, as a barrier. So dia akan act as a barrier. As a barrier because of a different orientation. Okay, you tengok kat sini all these crystallities have a different orientation to adjacent grain. Semua dia punya apa ni? Dia punya orientation of lattice structure semua berbeza. Okay, so different orientation. So let's say that we have a dislocation from here, from A. So we have a different dia punya orientation, katalah macam ni. Okay, let's say that we have a dislocation move from here, from A to B. So different orientation, passing from grain A, let's say, for example, that dislocation move from A to B. Then what happened is the dislocation have to change direction, and the atomic disorder within grain boundary will result in a discontinuity of a slip plane. Okay, katalah dislocation kat sini kan, tukar color je. Okay, katalah dislocation tu dia punya orientation macam ni. So bila dia sampai dekat sempadan ni, when this direction move toward the boundary, what happened? This dislocation cannot pass through the adjacent grain because this B have a different orientation compared to A. So what happened? Dislocation dia akan stop dekat boundary ni. Okay. So that is what I mean by this statement: atomic disorder within grain boundary. Okay, atomic disorder that happen here in the grain boundary will result in discontinuity of a slip plane. Slip plane ni dia akan stop dekat boundary ni because of different crystal orientation of grain A and grain B. Okay, grain boundary are barriers to slip or dislocation movement. So dislocation will stop here. It will not be able to move to the next grain. To move beyond this boundary. And barrier strength increase with a misorientation. Lagi banyak dia punya misorientation between grain A and grain B, the stronger the barrier. Lagi susah untuk dislocation ni to pass through the boundary. Okay, when we have a grain size, smaller grain size, then we have more barriers to slip. Okay, we have an equation that we call as a Hall patch equation that relates the grain size to the yield strength. Okay, kita ada equation ni. Equation ni dia mengkaitkan antara grain size dengan yield strength. So ini kita punya yield strength. Okay, this is our yield strength. Sigma tu, you still remember, is yield strength. Okay, so this is a strengthening coefficient. K is a strengthening. K sub y is a strengthening coefficient. And this is the average grain diameter D. The square root of D. Okay, the Hall patch equation is not valid for material with unusually large or ultra fine grain. Okay, kalau grain dia tu besar sangat ataupun too small, then Hall patch equation is not valid if we want to determine the yield strength. Okay, is fine grain material harder and stronger than coarse grain material? Why? What do you think? Fine grain, let's say we have a fine grain versus larger ataupun coarse grain material. Okay, which one is harder and stronger? Mana satu yang kuat? Bila kita ada dua material, satu yang kecil-kecil, fine grain, versus larger grain material. Which one do you think is harder and stronger?
Larger.
Kecil Siapa jawab tu?
Ain.
Ain. Okay, betul because fine grain material has a greater total grain boundary. Okay, kalau smaller grain boundary ni makin banyak lah dia punya sempadan tu. So makin limited dislocation tu dia nak bergerak. Banding dengan, let's say kita have a larger grain size, dislocation will still move in far distant compared to smaller grain. Okay, so larger grain size material dia lagi ductile daripada smaller grain size, tapi smaller grain size metal, for example, will be harder and stronger compared to larger grain size metal. Okay, so in short, when we reduce the grain size, we increase the number of a grain and hence increase the amount of a grain boundary area. So any dislocation move only a short distance before encounter a grain boundary and the strength of metallic material is increased. Okay, ini yang macam saya kata tadi. Okay, I think I skip this. Okay, if we have a high angle boundary, dislocation may not cross, but rather concentrated around it to create a new dislocation at the neighboring atom. Okay, high angle boundary ni macam ni lah, a very different orientation from the adjacent grain. Okay, then what happen? Dislocation dia akan terkumpul dekat boundary tu. Okay, the smaller grain mean more grain. Okay, look at this figure here. So this is a 70 copper, 30% zinc, brass alloy. Okay, if you look at this figure, what can you conclude? Let's say we have a larger grain here, and here we have a smaller grain on your right. We have a larger grain on your left, smaller grain on our right. So what can you conclude here? If you look at this graph. Apa yang you boleh nampak kat sini? Okay, ini punya yield strength. What can you conclude from this graph? So nampak strength ni makin naik kan? Okay, when we decrease the grain size, okay, the strength increase. Okay, what happen if we increase the grain size? Then the yield strength will decrease. Okay, so that is something that we can observe here. We can see that the strength or the yield strength increase as the size of grain decrease. Okay, yang ini lagi kecil daripada yang sebelah ni. Okay, this is the whole patch equation yang saya just mention tadi. Okay, so in general, fine grain is stronger because adjacent grain have a different orientation, and so dislocation have to change direction. Change in direction is harder if large misorientation exists. Smaller grain size also mean that atomic discontinuity atomic discontinuity. And then what happened is slip plane will be discontinued. So in general, fine grain is stronger, harder, more tough compared to small, larger grain, and more susceptible to strain hardening. This is the example of a dislocation pileup that I have mentioned before. Okay, when we have a slip plane, what happens if it cannot cross to the next grain? It will accumulate at the grain boundary. So this is a pile-up model, a pile-up. And this is a pile-up model that state the dislocation are moving inside the grain until they reach the grain boundary that stop their movement. So we have a figure here. We can see this is a figure that shows a dislocation pile-up model. So since the dislocation cannot pass the grain boundary, kita tengok kat sini. So what happened? This dislocation atau slip plane ni. Dislocation cannot pass the grain boundary because of the mismatch of between the grain. We have a grain boundary that act as an obstacle. So slip plane ni ataupun dislocation dia akan terkumpul dekat boundary ni. So this is the pile-up model. Okay. Okay, another way, if we want to improve the strengthening mechanism, improve the strength of a material, we can also perform solid solution strengthening. Okay, another way to strengthen and harden metal by alloying with impurity atom. So I think you already know we have two types of impurity atom. For example, we have many types, but here I just mentioned two: substitutional and interstitial. Okay. This strengthening via solid solution formation caused by increased resistance to dislocation motion. So this is the reason why we have brass, zinc, copper, zinc alloy stronger than pure copper. Okay, carbon alloy plays a role in the strengthening of steel by forming iron carbide. And also tukang mas, jewelry could be made out of from pure gold or silver, but pure gold and pure silver are extremely soft and malleable. So if you want to increase the strength of pure gold and pure silver, so tukang mas dia akan letak sedikit copper to gold and silver to make sure that the jewelry will retain its shape. Okay, I think I just stop here until this solid solution strengthening because I already made a video about the rest of this topic. I will share with you the link later in the group. Okay, so for any question for strengthening mechanism? Minggu depan kita ada test satu. Boleh tak ada test satu minggu depan?
Boleh.
Boleh. Okay, saya akan share sambungan to strengthening mechanism ni. Saya akan bagi link dia. So any question? Nak tanya?
No.